In this video, we are going to finish the chapter on sound, and we're going to start by talking about the Doppler effect. And so the Doppler effect comes into play when we have objects moving that are creating sound waves, whether it's the observer that's moving or the source that is moving. Let's consider a fire truck here that is stationary and at rest, and it blows its siren and it creates this wave front. And the wave is going to propagate as pictured here in these blue wave fronts. And the space between them is going to be consistent. This space is going to be the same because that is the wavelength. All right, and these blue lines represent the condensations, or you can think of them as the crests of the wave. And so the space between those crests, or the space between the high pressure points, are all going to be the same. However, if we make this truck move to the right, now as it's moving to the right, it's still propagating these same sound waves, but the issue is on the right, we get a condensed wavelength. The wavelength is smaller to the right because it's moving to the right, so when it releases its second condensation, it's closer to the first one, and so on. And behind it, we see a larger wavelength. So how this affects us, or how we perceive this, we call this the Doppler effect. And what it is we see this as a change in frequency. When we have a shorter wavelength, we hear it as a higher frequency, which means a higher pitch. And so the Doppler effect is the change in frequency or pitch of a sound detected by an observer because the sound source or the observer, or both, are moving with different velocities with respect to the medium of sound propagation. So they are moving, either one or both are moving, the detector or the source is moving, and so we notice this higher frequency or lower frequency. Notice when the source and the detector are coming together, so whether the source is moving to the detector or the detector is moving to the source, we see a shorter wavelength, higher frequency, higher pitch. When they are moving apart, as over here on the left, we see a larger wavelength, lower frequency, or lower pitch. So if we look at this motion of the truck, we can see that the regular wavelength that the truck is going to release, we're just going to call lambda. However, the wavelength that the observer sees, we're going to call lambda prime. And it's going to be shorter. It's going to be shorter by the velocity of the truck times the period, t. So if we write that lambda prime is equal to the original lambda minus vst, where vs is the speed of the source. Make sure you understand that speed of the source, not speed of sound, it's speed of the source. So it's the speed of the fire truck here. Then we can do a little algebra and we can solve for our frequency of the observer. What the frequency observes, well, that's v over lambda prime. And doing some algebra here, we see that we can simplify to the frequency of the observer is going to equal the frequency of the source multiplied by this expression right here of 1 over 1 minus the velocity of the source divided by the velocity or the speed of sound. So this v right here is the speed of sound in those conditions. Now this was for this specific case of the truck moving toward the observer. So let's generalize a little bit in saying that a source moving toward a stationary observer, we know that the observed frequency is going to equal the source frequency times this ratio of 1 over 1 minus Vs divided by V. Now, what if the source is moving away from the stationary observer? Then all that changes is this minus becomes a plus. And so the key to remember here, if we're moving toward, we would expect the frequency of the observer to be higher than the frequency of the source. And in the object moving away, the source moving away from the observer, we would expect a lower frequency. So we want to make sure we can check our math there to see, did we go up when we should? Did we go down when we should? Let's look at an example here. We have a high-speed train that is traveling at a speed of 44.7 meters per second when the engineer sounds a 415 hertz warning horn. The speed of sound is 343 in these conditions. And what are the frequency of the wave and the wavelength of sound as perceived by a person that's standing on the crossing while the train is approaching and while the train is leaving the crossing? So we're going to use both of these equations here in the approaching and leaving, where we see an increase in frequency and a decrease in frequency. And so for the approaching, we use the first equation and we put in the 415 hertz here for the frequency of the source, and then the speed of the source divided by the speed of sound. We take that ratio away from 1 and then reciprocate it, and we get 477 hertz. Now, as it's approaching, we would expect it to be higher. 477 is higher than 415. Okay, we did this correctly. We used the correct formula. Now let's see when it's leaving. What is it going to do? Well, we would expect it to be lower than 415 hertz. So using that formula, plugging in the numbers, we get 367 hertz, which is in fact lower than the 415. One thing to point out here is this is not a linear difference, in that the amount of increase in the frequency is not the same as the amount of decrease, even though the speed is the same. We increased here from 415 to 477 by 62 hertz. So we see an increase of 62 hertz as it's approaching us, but we see a decrease in the frequency here of 48 hertz. So try not to have the preconceived notion that, well, since the train's moving at the same speed, it's going to increase the same amount and decrease the same amount, whether it's approaching or leaving. We have to let the formulas guide our thinking. Now let's look at the situation where the source is staying stationary, but the observer is moving toward the source. Well, the same sort of thing happens in that the source is spitting out this wavelength that is constant. However, we have a velocity toward the source, and so we're going to shorten that wavelength. We're going to experience each waveform a little sooner than what the source intends. And so once again, we're moving toward the source, just like the source moving toward us. We would experience a higher frequency. So using the math here, looking at the frequency is going to increase by the speed at which the observer is moving divided by the wavelength. Well, we find that the frequency observed is equal to the frequency of the source times 1 plus the ratio of the speed of the observer and the speed of sound. So to once again generalize, an observer moving toward a stationary source, we're going to have this equation that the frequency observed is equal to the frequency of the source times the quantity of 1 plus the ratio of the speed of the observer and the speed of sound. But what if the observer is moving away from a stationary source? Well, once again, we would expect the frequency to decrease, and so all that changes is this plus goes to a minus. Now, there are 4 equations here with the Doppler effect because of the 4 different situations, whether we have a stationary source or a moving source, and which direction is the movement. So we can generalize this and create a general case that works for all 4 cases and then some. And we can combine those 4 equations into one kind of simple but a little complicated, in that we can say the frequency observed is equal to the frequency of the source times this little ratio here. Now, what does this ratio mean? Well, the numerator is talking about when the observer moves towards the source. So we use a plus sign if the observer is moving towards the source. If the observer is not moving, then this just becomes a 0, and we're just left with a 1 up top. Whereas the denominator, we have a minus sign that applies when the source moves towards the observer. And so that is one tricky part. It's a little backward here compared to the numerator. But once again, if the source isn't moving, that gives us a 0. And so we just have a 1 in the denominator. And so this general case can simplify to all 4 of those other cases. Now, sound can be used in a lot of different fields. The Doppler effect is actually used with sound and with light. We use the Doppler effect in Doppler radar when we want to look at weather systems. In in astrophysics, excuse me, we use the Doppler shift to look at faraway galaxies and to see are they moving toward us or moving away from us. Now, we're not using sound in that case, we're using light, but light acts the same way and shifts the same way as sound in that the wavelength either increases or decreases depending on the direction it's moving. Some other applications of sound are in medicine, and we can use ultrasonic waves and we'll use that to image parts of the body. A lot of times this is used to image um, infants, before they're born, while they're still a fetus. And so we can image the baby to check, is development going all right, or are there issues that we may see coming down the pike. Um, we can also use we can use ultrasonic sound to break up tumors or possibly detach tumors. So this is used to, whether we want to kind of cut a tumor away. We can use a physical scalpel, or something a little less invasive would be an ultrasonic pulse that can be used to break that tumor from the tissue. Or sometimes we use them to break up things like kidney stones or stuff like that we want to shatter into smaller pieces. We can also use the Doppler shift to get flow rates of our blood, and we can measure to see how fast the red blood cells or white blood cells are flowing through your veins based on it's sending a pulse, bouncing that off, and receiving it, and we can see the shift, and we know how fast these blood cells are moving through your veins. Last thing I want to put up here is looking at the intensity level and the frequency and how they correspond here with the sensitivity to the human ear. As you know, there's a range in which we can detect sound. We have to be within the threshold of hearing, and then we get up to the threshold of pain potentially, or we get to a frequency that we just can't even hear, even though it's not painful, we just can't hear it. So there is a linear relationship in the frequency. There's a range that we can hear, but there's also a relationship with the intensity level. And so this curve kind of denotes that, okay, a frequency of 40 hertz, we can't hear it unless it's up at an intensity level that's, close to 60 decibels. And so, the at its core, the 40 hertz is a pretty low frequency and tough for us to distinguish. But if it's loud enough, yeah, we can hear it. Also, when we get up into this range of 1,000 hertz, we can start to hear that just around 0 decibels, or even just a tiny bit higher than zero. And so these curves help to show us, how the intensity level and the frequency are related, and what we can hear and what we can't hear.